Welcome students. In this lecture we shall prove that every convergent sequence is a bounded sequence but converse is not true. This is our fourth lecture on real analysis. If you want to watch my another videos on real analysis, you can visit my playlist. Consider we have a sequence Sn and Sn is a convergent sequence, that is Sn converges to some limit L. We need to prove that Sn is a bounded sequence. For bounded sequence, we need to prove that there exists a lower and upper bound of Sn for all natural number n belongs to n. G is a lower bound for the sequence Sn and capital G is an upper bound for a sequence. We need to prove this relation. Now, as Sn converges to L, we can write it as in the form of limit, that limit n approaches to an infinity Sn equal to L. Now we apply the definition of limit, which is Sn minus L mod is less than epsilon for all n belongs n greater than or equal to m. Now we can write it as minus epsilon is less than Sn minus L less than plus epsilon for all n greater than or equal to m. Now the reason is, as when x mod is less than a, we can write it as minus a less than x less than plus a. Now from here we can write, if we add L on all three sides of this inequality, we get L minus epsilon is less than Sn less than L plus epsilon, and this relation holds for all a natural number n greater than or equal to m. Now from this relation we can write L minus epsilon is less than Sm, as this relation holds for all values n greater than or equal to m. So this relation holds for m, and that's an L plus epsilon. Similarly, this relation holds L minus epsilon is less than Sm plus 1 less than L plus epsilon. The reason is this relation holds for all values n greater than or equal to m. This relation holds for Sm, this relation holds for Sm plus 1 because m plus 1 is greater than or equal to m. Similarly, we can write L minus epsilon is less than Sm plus 2 less than L plus epsilon. Now this process continues for infinitely many values of Sm. So for all values n greater than or equal to n, we can find this relation. Now our target is to find a lower and upper bound for this sequence. Now we choose a lower bound for this sequence. Let small g is equal to minimum of L minus epsilon and as L minus epsilon is less than Sm, L minus epsilon is less than Sm plus 2, L minus epsilon is less than Sm plus 1, Sm plus 2, up to so on infinitely many values. But In this sequence, we do not have terms like Sm minus 1, Sm minus 2, up to so on, S1, S2, S3. So I insert these terms which are missing, which are S1, S2, up to so on, Sm minus 1. Now, in this equation, if g is equal to minimum of these values, then all the values are covered, because L minus 1 is less than Sm, Sm plus 1, Sm plus 2, up to so on, infinitely many values which are greater than m. And the terms which are not covered by L minus epsilon are S1, S2, up to so on, Sm minus 1. So if g is minimum of these values, then g is less than or equal to Sn for all n belongs to natural number capital N. This is our equation number 1. Now, in the similar way, we find an upper bound. Let capital G is equal to, now I replace L minus epsilon by L plus epsilon. This is capital G is equal to maximum of the terms L plus epsilon. Just I replace L minus epsilon by L plus epsilon, and the rest of terms remain same, that is S1, S2, up to so on, Sm minus 1. And the logic is same as we concluded for this G equal to minimum of L minus epsilon, S1, S2, up to so on, S minus 1. Because if G is equal to maximum of L plus epsilon, so all the terms of this sequence are less than L plus epsilon, and the rest of the terms are S1, S2, up to so on, Sm minus 1. So if G is maximum of on these terms, then we can write Sn is less than or equal to capital G for all natural numbers n belongs to n. This is our equation number 2. Now from 1 and 2, from equation 1 and 2, we can write small g is less than or equal to Sn, and Sn is less than or equal to capital G for all natural numbers, small n belongs to capital N. And now this is the definition of bounded sequence. G is a lower bound for this sequence, capital G is an upper bound for this sequence, which implies Sn is bounded, which implies every convergent sequence is bounded. Convergent sequence is bounded. Now we discuss the converse of this theorem. Converse of this theorem is not true. Consider an example. Now we choose a sequence which is bounded but not convergent. Let Sn equal to minus 1 raised to the power n. The terms of this sequence are like, when n is 1 we get minus 1, when n is 2 we get 1. So the terms of the sequence are minus 1 plus 1 minus 1 plus 1. This is an oscillating sequence of infinitely many terms. Clearly this sequence is bounded. The reason is all the terms of this sequence are less than or equal to S. Minus 1 is less than or equal to Sn, and Sn is less than or equal to plus 1, which implies Sn is bounded. Now this sequence is bounded, but this sequence is not convergent because limit of this sequence does not exist. Limit n approaches to infinity minus 1 raised to the power n. This does not exist.